Okay, so here is the material for the third exam, which is only cardiovascular, the circulation stuff, including capillary action and blood vessels, and then erythropoiesis and all of the stuff about red blood cells. So because it's only 2 lecture packets, even though there's a lot of stuff in there, I've tried to make the questions be a little bit more sort of going for the details, a little bit more in-depth. So it's hopefully getting more at the material that's all there. All right, so for the first one, for the heart, you have to know, obviously the anatomy of it and all the blood flow, and the differences in function between the atria and the ventricles. So I made a big deal out of saying that the atria really, their role is to squeeze a little bit of extra blood and a little bit of extra pressure on at the end, and they're not the main filling pumps of the heart. There are layers to the heart, so from inside to out, it's myocardial cells, or the muscle cells, kind of like the middle portion. There's an endocardium and there's an epicardium that form the rest of the sandwich. Most of what you see in the heart are muscle cells and ones that contract and generate force, but there's also cells that either propagate the action potential or are the spontaneous action potential initiators in the first place, and those are the pacemakers and the nodal cells. You have to know all 4 valves by multiple names. So right and left AV or atrioventricular valves are also known as tricuspid and mitral, and those are these valves right here, and they generally have blood coming down from the atria above, draining into the ventricle, and when the ventricle squeeze, the pressure is going to try and push blood backwards, and so all of the anatomy here is to prevent backflow of blood from going out there. So it's reinforced by the chordae tendineae, which are these things right here, and then the papillary muscles attached to the bottom of the ventricle, and so these contract the same time ventricles do, and they try and tighten this so that there's no way that blood can go back. All of the valves open passively just by blood pressure. There's no mechanical things opening or closing them. There's no tendons that open or close them. They're, even these muscles here don't open or close them. They just provide extra support. So everything is just passive blood flow. The semilunar valves, also known as the pulmonary and the aortic valves, which is the blood vessels that they serve, are slightly different shape. Here you would have blood in the ventricle coming upwards and out into the major arteries. If blood turns around and falls back, it sort of cups the little cusps here, and then that closes the valves. There were failures to the valves, so they should open smoothly and they should close tightly. If they don't open smoothly, maybe you've got plaque or stenosis, then that is a narrowing valve, and that is a murmur that you could hear as sort of turbulence during ejection. If the valve doesn't close all the way and blood goes gurgling back into the chamber below it, that would be sort of a noisy sound after contraction had completed, and so that would be an insufficiency. The conduction system of the heart, you just have to know it in order. So the sinoatrial node is first. It is in the right atrium. It spreads over to the left atrium as electricity, and then the AV node picks it up, and the AV node has the very important function of delaying the electricity. So while the atria have contracted and the electricity starts coming down here, it waits up just for a little bit, and that gives the ventricles time to maximally fill with blood. The electricity goes down through the bundles and then around through the Purkinje fibers, and you have from the bottom up to the top electricity, and therefore from the bottom up to the top squeezing of blood out through the ventricles. The ventricular action potential has a different shape, different values for the voltages over here, and even different ion channels involved in it. So first off, the resting membrane potential is at -90. That's really low. Peak potential is at about +20. The voltage gated sodium channels give you the rising phase here, and then they close, and then a new channel, the slow L-type or long-term calcium channels, which are voltage gated, open, and they kind of catch this and hold it at this plateau for about 1/4 of a second, and then they close and the voltage gated potassium channels open, and you get the falling phase or repolarization. So this is what it would look like in the ventricles. The initial depolarization right here would come from a graded potential, which would be the nodal action potential coming through the Purkinje fibers by the time it reaches the ventricle. Okay, so it's called the nodal action potential here because it does start in the SA node, but by the time it gets to the ventricles, it's actually propagating in the Purkinje fibers. At any rate, it also is unusual looking compared to normal muscle and nerve. It does not have a flat baseline here. It has this constantly ascending potential, which, you know, they say resting, but obviously it's not resting. It's constantly aiming for a threshold, and that makes it spontaneous and autorhythmic. When it gets to its own threshold, which is at -40, you have an action potential, and then it goes down, then it goes back up to its own threshold, action potential. So it is self-energizing. It doesn't need anything else to make it go from here to here. It does it all kind of by its own creation. There are 4 voltage-gated channels which create the nodal action potential here. And there's a sodium channel and potassium channel like we've always had. There is a long-term calcium channel like we had in the ventricle, but then we have an even newer additional one, which is the fast T or transient calcium channel. So these 4 things give you this. All right. So from here to here is the responsibility of the voltage-gated sodium channel. So here's a little bit of sodium coming in. That gives me this. Then the fast calcium channel right here in green makes you go from here to here, so it achieves threshold. And then most of the shape of the action potential here is from the slow calcium channel. And then the potassium channel here opens. This is it opening, this is it closing again. It would open, gives you repolarization back down to here. So constantly going to threshold, get an action potential, constantly going to threshold, get an action potential. So voltage-gated sodium channel, fast calcium, slow calcium, and a potassium channel. So there's 4 there. There's 3 for the ventricle and only 2 for everything else we've ever seen. All right. Heart rate down here is influenced by nerves, which innervate both the pacemaker regions of the heart and also the contractile muscles of the heart. You would have the sympathetic side over here. You have the parasympathetic side over here, and this would tend to decrease heart rate, and this would tend to increase heart rate. The chemicals for the sympathetic side are norepinephrine. For the parasympathetic side, it's acetylcholine. The receptors are beta-1 for the heart, and then muscarinic for the parasympathetic. The result of norepinephrine binding to beta-1 receptors is you get more sodium and more calcium coming into the heart. So that's going to depolarize it more. That's going to increase the rate of depolarization, and you're going to have a faster heart rate. And so this is influencing the SA node and the pacemaker regions. That's what we're talking about here. There are some other things elsewhere, but this is for the nodal portions. Okay, if I wanted to slow down the heart rate, acetylcholine would bind to the muscarinic receptors. It would increase potassium leaving the cell, so that hyperpolarizes me, and it would prevent calcium from coming in, which makes it less depolarizing. And so these 2 things together hyperpolarize the cell, slow down the heart rate, slow down the SA nodal activity. All right. If you look at the EKG or electrical activity in the heart, you can see some patterns. And this looks like a depolarization, this looks like a depolarization, this looks like a depolarization. So this is the P, the QRS, and the T waves or complexes. This corresponds to atrial depolarization, so SA node. This corresponds to AV node bundles Purkinje fibers. And then this corresponds to repolarization of all that mess. And we don't need to get into why it looks like it's going up instead of down. It's not really important for us. By looking at the electrical activity in the heart, you can notice abnormalities. And the abnormalities include things like some of the waves missing, like here you don't see the waves, extra things happening sooner, disjoints between the SA node and AV node, like in heart block and all different types of things. So just some patterns that you've now seen. All right, the mechanical events of the cardiac cycle. You have to know the 4 phases of the heart cycle. So this goes around and around like an engine. And phase 1 is filling of the ventricles. Then phase 2, the ventricles contract, but they don't have enough pressure to eject the blood. Phase 3, you have blood leaving the ventricles. And then phase 4, the ventricles need to relax before they can open up and let new blood come in. So phase 1, 2, 3, and 4. These 2 periods right here are considered diastole, where the muscle is not actively contracting. And these 2 phases right here are considered systole, where the muscle is squeezing. Even if I don't have blood leaving, I still can squeeze and pressurize the blood in isovolumetric contraction. So here is the heart cycle. Don't forget there is text here. It's hard to see, but it says isovolumetric contraction right here. Here is a Wigger's diagram showing 2 complete cycles of the heart. You have up here 3 different blood pressures. One of the blood pressures is in the aorta, one of the blood pressures is in the atria, and one of the blood pressures is in the ventricle. Anytime these blood pressures intersect one another, you will have the event of a valve opening or closing. The aortic blood pressure is pretty simple. It's just when the ventricle ejects blood, the pressure goes up. When the ventricle is no longer ejecting blood, the pressure just falls and falls and falls. So this is true diastolic pressure in the aorta, and this peak is true systolic pressure in the aorta. The red line here is ventricular pressure, and it gets a little bump from the atrial filling at the end of late diastole. Then it squeezes blood and it ejects blood, and then it relaxes. Now, even just looking at the ventricle and the aorta, there's a couple of events you can see. Before the blood can leave the ventricle, it has to equal the blood pressure in the aorta, and the aortic valve will not open until those 2 pressures are equal. So this is a phase of the heart where I'm squeezing but no blood is leaving, and that's isovolumetric contraction. This phase here where blood is leaving the heart is ventricular ejection, but there's a point where I run out of pressure and the aortic valve closes, and this begins isovolumetric relaxation. But before new blood can come in, this pressure has to subside down to equal the atrial pressure, and then you can have opening of the AV valve. This whole phase right here would just be slow return of blood to the ventricle. Here is the atrial contraction. So this is early ventricular filling. This is late ventricular filling, or passive filling and active filling. And here the atria contract and gives a little bit of pressure and a little bit of blood. Okay. As soon as the ventricle contracts, it closes the AV valve, which is marked right there. So AV valve closes, aortic valve opens, aortic valve closes, AV valve opens. This is the end of phase 1. This is phase 2, phase 3, phase 4, and this is all phase 1 right there. Okay. This is volume of blood in the ventricle, and this is the equivalent of ejection of blood as you stroke it out. This is passive filling, just blood draining through the atria into the ventricle. This is active filling, where the atria squeezes and puts blood on top, and then ejection again. This matches up with the EKG. The P wave occurs before atrial contraction. The QRS complex initiates ventricular contraction, and you hear heart sounds anytime the valves close. So the first heart sound is when the AV valves on both sides close. The second heart sound is when the semilunar aortic and pulmonary valves both close at the same time. Okay, so here's a complete heart cycle with all the timings in here for the outline version. One of the most important intrinsic properties of the heart is the Frank-Starling law. It is a length tension curve just like we have for skeletal muscle, except this is in cardiac muscle, with the exception that the optimum length, which would be the most force you could possibly get out of cardiac muscle, is a place that the heart does not operate at. So it instead works way down here, where it's not getting the maximum force out of the muscle. So that seems suboptimal. But the benefit of being down here is that should the heart get stretched and distended more and more and more, it has the power to get more blood out at the same time. So if you put more blood in, you get more blood out. Put more blood in, you get more blood out, up to a point. And here, at its optimum length, if you go over here, now I put more blood in, I get less blood out. Put more blood in, I get even less out. So this portion right here is not where you ever want to be as far as the pumping function of the heart. So this is where you are if you have dilated or congestive heart failure, or sometimes called backwards heart failure, and you can see the volume of blood in the heart is getting bigger and bigger and bigger, and you're just dilating it and dilating it and dilating it. The axes here, this is end diastolic volume, which is right before systole, therefore this equals preload or filling of the heart. This axis right here is stroke volume, and it's just how much blood you get ejected, and it's never equal. You don't put in 200 mils of blood and get 200 out. It's, you know, half or a little bit more at best in humans. Okay. All right, so cardiac output as a volume of blood being pumped per minute is just the product of heart rate times stroke volume. If your heart beats faster, usually cardiac output goes up. If your stroke volume is higher, your cardiac output should be bigger. The way to calculate stroke volume is to take filling minus emptying. So end diastolic volume minus end systolic volume gives you stroke volume. Cardiac output as a more complicated product is influenced by lots of different things. So because multiple things influence heart rate, multiple things influence cardiac output. Multiple things influence stroke volume, so therefore these things all can affect cardiac output as well. For Frank Starling's law of the heart, that's this one right here, end diastolic ventricular volume, that's an intrinsic property of the muscle. Sympathetic nerve, so that's an extrinsic, so it's coming from outside the heart. So if you have nerves that influence beta 1 receptors and you get more calcium, that gives you greater stroke volume. If you have blood, epinephrine, that goes to the heart, you also get greater contractility and calcium. So this is all calcium-based beta 1 receptors giving you more depolarization and more contractility. Both of these nervous things, as far as epinephrine, would also affect the SA node. You also have more calcium coming in, and therefore a faster depolarization, and so heart rate increases. So you get kind of a double whammy from the sympathetic. Stroke volume is affected and heart rate as well. For the parasympathetic system, the only mechanism that these nerves have is to slow down the depolarization of the SA node. So they don't influence stroke volume or muscle force at all. Okay. All of the things that do influence stroke volume, so end diastolic volume minus end systolic, things related to filling and time of filling. So filling time, filling pressure, how's your blood volume, are you standing up or lying down, are you exercising, all those things will influence preload. And systolic volume is affected by resistance to getting blood out, that's called afterload, and how strong the heart muscle squeezes, which is influenced by sympathetics like epinephrine and norepinephrine, and Starling's law of the heart, which is just the intrinsic contractility. Here's preload and afterload demonstrated. Preload is filling and stretch of the ventricles, so that's end diastolic volume. Afterload is when the ventricles are trying to get blood out through the pulmonary trunk or through the aorta. Are the valves working? Do they open smoothly? Is there back pressure from hypertension? Is there viscosity issues with the blood? All those things would influence the resistance to getting blood out. So this is preload and afterload, and this is huge in most heart pathology. So things will be wrong with either of those two. There are sensors in the carotid arch which detect blood pressure going to the brain. You want to have just the right blood pressure, not too much, not too little. If you have a lot of blood pressure, then the stretch of these blood vessels right here is big, and that's sensed by the vasomotor sensor, and you dilate this entire tube here, and that takes blood pressure away from the brain. If you stand up real suddenly and you get dizzy because you don't have a lot of blood pressure, then these whole then the stretch here is not enough, and the blood vessels here tend to constrict to try and force blood up to the head and increase your delivery pressure to the brain. Okay. For circulatory function, a lot of this has to do with capillaries. There is some stuff with a tissue that needs blood gets it, a tissue that isn't, really using blood doesn't need to get it. So you can adjust these things. You can turn them on, you can turn them off. For blood flow, flow is related to the delta pressure. So how much pressure do I have at one end of the tube, how much at the other? So this is a drop of 50 to 10, that's 40. Here's a drop from 90 to 10, that's 80. So this is greater flow. So flow is proportional to the pressure difference. Flow is not related to just the number of the pressure. So, 90 to 10 is a drop of 80. 180 to a drop of 100 is still 80, even though the numbers look bigger. So it's proportional to delta P, not the absolute pressure. The biggest thing influencing flow through a tube is the radius. Is the radius 1? Is the radius 2? What's happening to the flow through the tube? Without getting into the nitty-gritty of it, the relationship between radius and flow is radius to the fourth, which means that if you change the radius from 1 to 2, you go 2 to the fourth, which is 2 times 2 times 2 times 2, which is 4 times 4, which is 16. So changing the radius a small amount has an enormous effect on blood flow. And so flow is proportional to the radius, and the resistance in the tube is inversely proportional to the radius. So small tube, high resistance. Big tube, low resistance. All right. As far as fluid at the capillary leaving to go supply tissues, the capillary endothelium by and large is very porous, so there's holes for water to just come out of the plasma and deliver things like sodium and glucose and ions and stuff. Gases can diffuse right across. Most plasma proteins stay in the blood, and there's a few things that get exchanged across the membrane. But by and large, capillaries are very leaky when they want to deliver things to tissues. The leakiness means that water is going to leave the capillary at one end and come back in at the other end, and that is governed by these four forces. The four forces that control water movement in the capillaries include capillary hydrostatic pressure, which is pushing water out from the blood. The resistance to that, which would be interstitial fluid pressure, already occupying that space. Oncotic pressure, because there are a lot of proteins in the blood that can't get out, and therefore water would want to come in. And oncotic pressure for the few proteins sort of moving around in the interstitial fluid here. So you add all these up at the arterial end of the capillary, and this sums to filtration being favored, moving water out of the capillary. At the venous end of the capillary, after it's gone through the tissue here, it has encountered a lot of resistance and the blood pressure is lower. Everything else is the same, but because the blood pressure drops, this means that you now favor reabsorption of water back into the capillary, which is great because all the water you just pushed out comes back in, or almost all of it. The rest is sort of scavenged up by the lymphatics, and these things are called the Starling's forces for capillary function. All right. If you want to summarize all of the influences that the parasympathetic and the sympathetic system have on blood pressure, the parasympathetic system can only affect heart rate, and it will drop cardiac output and therefore blood pressure, but it's only working on rate. The sympathetic side can work on heart rate, contractile strength, it can cause vasoconstriction of the arteries, it can cause vasoconstriction of the veins, and so there's a lot more factors under the influence of the sympathetic system that would boost blood pressure. All right, then the blood lecture for mostly red blood cell diseases. You should know hematocrit, which is just the volume of red blood cells after you spin them down compared to the whole thing. It's a little bit higher in men than women because of testosterone. The components of blood include the plasma as well as the cellular things. In the plasma, you have water. You have ions, sodium, potassium, chloride, whatever. You have vitamins and mineral, and you have the blood gases, oxygen and CO2, and then you have a ton of organic molecules, which could be glucose coming from the stomach, moving back and forth from the liver, lipids going from adipocytes or from digestion, nitrogenous waste going back and forth between the cells and the kidney, amino acids. All these different things are certainly being transported in the plasma. And then lots of blood proteins, and most of these are made in the liver. There's albumins, globulins, fibrinogens. So these are, clotting factors and immune factors and transport proteins. All those are in the blood. There were cellular portions too, but that I didn't show that slide. Erythropoiesis is the development of red blood cells from stem cells, which are in all those different locations in the bone marrow. The things that are required to make stem cells into red blood cells include the hormone erythropoietin, building blocks like iron, folic acid, and vitamin B12 for making DNA, and some sensation. So you don't want to make too many red blood cells. So there is kind of a negative feedback working here. If you have sort of adequate oxygenation of the body, you don't do anything different. If you're a little bit low on oxygen, then the kidney might kick up your EPO and you might try and make some more red blood cells. So this whole process takes about 5 days. It goes through a bunch of intermediate steps, and the red blood cells at the end will have no nucleus, no endoplasmic reticulum, and they have that biconcave shape. The maturation of the red blood cells is called diapedesis. They last about 4 months. They're constantly being removed or broken down by the kidney and spleen. A reticulocyte is a immature red blood cell, but it's in circulation. It doesn't have the nucleus, but still has the ER. And then erythrocyte is the mature red blood cell after you go from this to the mature. Here are all the different sites of blood cell formation. So, it can be soft tissues, it can be the liver and spleen, then it becomes, predominantly the bones. But, kind of the older you get, the more it sort of shifts up here. So it's really the pelvis and the vertebrae and the ribs, not so much the long bones by the time you're about even your age. Things that can influence erythropoiesis: if you have kidney failure, you won't make EPO, so you can take recombinant EPO. If you don't have the precursors you need, like iron or vitamin B12, then that also will influence red blood cell production. So there's a lot of, simple factors that have to be present for all this. All right, all the different blood disorders by name, you should know them. So low red blood cell count is anemia. If it's too high, it's polycythemia. Pernicious anemia is the one that has intrinsic factor as an issue because you damage the stomach. Sickle cell anemia is the genetic disorder where one amino acid is incorrect, and so you get sickling where the hemoglobin sticks together. Porphyrias are iron disorders. Thalassemia is genetic issues with the hemoglobin gene, so different than sickle cell. Here you're missing the whole gene. Here the gene is just defective. And then fatalis, what am I saying? Erythroblasto, man, can't even think. That one, where you have Rh negative mother and then Rh positive child, and you can get antibodies against it. All right, so you have to know all these by name. We'll review some of them going through here. As far as anemias, these three things are the major anemias you can have by category. So aplastic is if you destroy the stem cells, so there's lots of things that do that. Hypochromic is if you don't have enough color, is what that means. So you're missing, hemoglobin, or you're missing iron, something like that. So you're not making the red portion of red blood cells. And then megaloblastic is when you have vitamin B12 or folate deficiency, and so your DNA is messed up. So here, stem cells bad, here iron or hemoglobin bad, here DNA manufacturing bad. The different examples of aplastic anemia: there's classical, myelodysplastic, and infiltrative. This is from radiation and chemotherapy. This is a virus or an infection, and this is some type of derangement in the DNA. All these probably best treated by bone marrow transplantation. Megaloblastic, you just don't have vitamin B12 or folate, just get vitamin B12 or folate and you're fine. Hypochromic was in there. If you don't have iron, just get iron. Okay. Pathology of anemia, basically no red blood cells, no oxygen carrying capacity, so that's the major one. The body has lots of ways of trying to boost either blood delivery or maybe try and make more red blood cells, whatever. That works, cool, then you've compensated. If not, then you have anemia. And full-blown anemia can task the heart, or it can make the heart work harder, so that's a strain on it. It can make the liver work overtime. You'll feel fatigued, you might feel lethargic, you might not have redness to your color, so you look pale. And your body might try furiously in the background to try and make it up, if it can, to boost your oxygen carrying capacity. What are the reasons why you might have compromised red blood cell production? So this is kind of messy, but what it's showing over here is these are things affecting the bone marrow. So this would be, aplastic anemia, infiltrative, and myelodysplastic. Over here you've got dietary things like maybe I'm not eating enough iron or vitamin B12, maybe there's something wrong with my intestine and it's not absorbing it, or I'm bleeding. Maybe here I've got gastric damage to the stomach. All those things will influence precursors. So you need the bone marrow, you need to have the precursors, and all of that will give you proper red blood cell production. Polycythemia, there's two examples. One is exercise induced and one is a genetic aberration. So both of these elevated red blood cell counts. Pernicious anemia is when you have ulcers of the stomach, you destroy the parietal cells which can't secrete intrinsic factor, and without that you can't absorb vitamin B12. So ulcer, no intrinsic factor, can't absorb vitamin B12, means you have not enough red blood cells. Okay. All right. Thalassemias, there's alpha and beta genes. These are components of the hemoglobin 4-part chain. If you are missing one, that's carrier, 2 is minor, 3 is HBH, and 4 is hydrops fatalis for alpha. For beta, it's either minor or major. The symptoms were, all these things here. Treatment is primarily through transplant or transfusion, if at all possible. Sickle cell anemia is a single amino acid substitution. It is triggered in people who have one bad gene only at low oxygen state. So, extreme exercise or on top of Everest or something, not even that, but at altitude, they might suddenly trigger a event where their hemoglobin begins to stick together and you get sickling of the cells. For people who have both bad copies, they have a lifetime of that. And so, transfusions and bone marrow transplant would be ideal treatment for them. Leukemias are issues with white blood cells. Blood groups, make sure you remember O, A, and B is just part of it. You also have to have the Rh positive and Rh negative addition. O blood has no surface flags on it. A and B have flags that say I'm A and B. You would make antibodies against things that are not you. So if you are type A blood, you would make antibodies against B. If you're type B blood, you make antibodies against A, so on and so forth like that.